Hey guys, I'm sorry. We're gonna get started. So if you want to keep talking, please go someplace else.
So good?
Yep.
So
It
I can just sit and troll you now?
absolutely. I have your T-shirt, so I don't know if you want to be trolling me, but all right. Question number one: who has been at JavaDay Kiev 2013? Okay, if you've seen this talk, it may be a bit boring. This is a repeat at request of the organizers. So if you've seen this talk before, you may not find it useful. We're going to be talking about some performance tuning. Who has ever seen talks by Alexei Shepilov from Oracle? Yeah, no, don't leave the room because unlike Alexei's talks, your eyes are not going to bleed after this one. You will still walk away with your sanity, and I'm not going to be talking about tuning individual things or how to turn a screensaver when you present, which is a presenter 101. But we're going to talk about how to use some of the free tools that you may or may not be aware already exist on your computer to find application problems. When do application problems typically happen? In the middle of the night when you're on call, I have those awesome stickers to give out to some of the best questions. One of them says, "Не регресс, как на праздник." And unfortunately, those things do happen during holidays. We also have some T-shirts. Thank you, JFrog. And we have one and one only T-shirt from Ex-Rebel. Anton is somewhere here. He'll pick the best person who asks the best questions. So here's what we're going to cover today. We're going to talk a bit about me. We'll figure out who we have in the room. We'll talk about some fundamentals of performance tuning and key concepts that you need to know. And we're going to spend the rest of the talk in live demos and debugging. So we'll try to solve some problems. So this is me. I've done this for about 20 years. I've been coding Java since 2002. I used to run engineering for an application performance management product at CA. And if you don't follow me, if you want to follow me, I'm at Ligolnik on Twitter. So let's figure out who we have in the room. Who here is a developer or identifies as a developer? All right, good. Team leads, tech leads? Okay, they cluster. Safety in numbers, Baruch, like always, like they're over here. Any managers? Okay, a couple. Architects? Okay, few. We'll skip this. So it's sure here. So let's see. Who here builds talks that are written in apps that are written in Java? Figures JavaDay. Any other language that runs on the JVM? Well, the good news, for those of you that don't write in Java, even though my examples are in Java, most of the tools that I'm going to show you still apply. JavaScript? What are you doing here? Any, God forbid, .NET? Oh, thank God. No, all my .NET jokes work. All right, so let's figure out what kind of scale you guys have to deal with. Who builds apps that are used by about 100 users a day or so? Or more than okay. Thousands of users a day? Tens of thousands? Hundreds of thousands? Millions? Okay, one. Oh. You don't count, Baruch. You don't code. I don't do surveys. That's why I didn't raise my hand. Anybody like that? Okay, at least a couple of people. All right. So performance tuning. Let's talk about some of the key concepts, right? And why is it important? I didn't have a more recent example, but I brought this one up. If anybody remembers, about 5 years ago, Facebook went IPO. Blah, big deal, big company. Unfortunately, it was botched pretty badly because the computer systems of the exchange in which they were listed, NASDAQ, the biggest exchange for tech stocks in the US, couldn't handle the load. They paid $10 million in fines for that. Right? Performance tuning can be pretty important, not just because your user can't send money to their mom or the other way around, their mom cannot send money to them when they want to. That has some real-life financial implications. So what is performance tuning? We're going to go to the source of all truths in the universe, not the thinker from the Hitchhiker Guides of Galaxy, but we're going to go to Wikipedia. And that's the definition Wikipedia will give you if you pull up the performance tuning page. It says performance tuning is the improvement of the system performance, obviously. Oh, wow. Can Can somebody from the organizers kind of try to see if there are any doors can be closed? That's kind of noisy. Typically in the computer systems, the motivation for such activity is called a performance problem, right? You typically want to know what you're trying to optimize. Okay. Real or the anticipated, right? And you know that most of the systems, as you load them up, will change their performance characteristic. They typically tend to work slower. There is exception to that rule, like any other rules. The key important things here is performance problem. So when you want to do any type of performance tuning, you got to understand what is that you're trying to solve for. More often than not, you hear things, system is slow. Like, what is slow? What are we trying to solve? Because you need to know that you've solved it, and therefore you have to be able to measure it. Right? Those problems can be either real. Somebody wakes you up in the middle of the night and says, hey, folks are trying to log into the website. It's slow. Or it could be anticipated. We believe that we need to handle this scale. I was trying to buy a new iPhone on the pre-sale day the other day. The store opens at midnight, and you can imagine how much traffic Apple and all the major telcos, storefronts have to handle on a launch of a big new phone, right? Performance tuning is typically done in a cycle that has 5 predictable steps, right? Step 1, you got to figure out what the target looks like. What's the acceptable behavior for what you're trying to do? And we'll have an example like that. Step 2, you got to be able to accurately measure the performance and do that reliably time after time. So if you don't have a good environment, you're not going to be successful. Another trick for doing performance tuning, has anybody tried to do some performance tuning on a laptop? I do it all the time because I fly a lot. Here's the trick. Don't forget to plug in. All kind of magic happens when your laptop tries to save battery and changes the CPU frequency as you try to tune a piece of code. So if you're trying to do this not being plugged in, that's a lesson for you. You're asking for some trouble. You have to be able to identify critical parts and the bottlenecks, and that's the main talk for this talk. Ideally, you're looking for the tools that don't require you to look at the code. Ideally, you want to find the tools, and remember this, we'll look through this time and time again. You want a vector into the code. Obviously, once you found what's broken, you have to be able to fix it. And then you have to be able to measure the performance again to know whether your fix actually created the desired result or not. Pretty simple, right? Establish acceptable performance criteria, measure system performance, identify critical parts or the bottlenecks. Sorry, broken slide. This build's not supposed to be here. All right. So, critical things to be able to do that. Knowing your tools. When I talk about knowing your tools, it's knowing the tools that you already get or knowing the tools that you can download for the job. A good friend of mine owns a construction company, and I walk to his truck every once in a while, and I see this array of drills on a shelf. I go, Andre, why do you have all those drills? Like, I have one at home, seems to be plenty. He goes, well, this is for concrete. This is for wood. This is super light when I have to climb the stairs to the roof. Similar things apply to us as software engineers. There are a variety of small little utility tools that we go and collect over the time we work. And knowing that is extremely important. Knowing your operating system, right? How do you know on your operating system or your operating environment, is the operating system spending its CPU cycles in user space or is it in system space? Containers are popular now. Who deploys stuff on Docker or at least develops on Docker today, right? Okay, few of you. Understanding how to understand and extract performance information out of your containers becomes extremely important. Otherwise, you won't be able to find what we'll define as a dominating consumer. Knowing your runtime, right? Most of the stuff here is written on JVM, operates on JVM. JVM is one of the more reliable, more mature language runtimes that we have today in our industry. Understanding the kind of tools it provides to you will save you in the middle of the night, right? When was the last time somebody looked at Java Home Bin? Who knows what's in there other than Java C and Java? What other tools are ever? Yes. What? Java P. What is that? It's a decompiler. Okay, what else? Any other tools over there? JConsole, all right. JPS. Who said JVisual VM? You may leave the talk. It's going to be very, very boring for you. I will give you a t-shirt, I think, for that. JMap. What does JMap do? JMap kind of does a heap dump effectively, right? And allows you to look at what's in there. All right, that's enough. Here's the listing. Right, there's plenty of tools. If you don't know what most of them do, you should spend a few minutes because one day they will save your butt. For example, if you're unfortunate enough to run your Java apps in the Windows operating environment, the most reliable way to get a reliable heap dump, which is at times essential to understanding what the hell is going on in your tool, is JStack, right? Let's demonstrate maybe. So I have this sample app, which is the app we will be what is going on? We'll open a new terminal. Are we in the right place? Yes, we are. All right. So I have this little app that runs. We'll talk about what it does later, but let's see, JPS. Let's get the fonts bigger so you guys can see. Right, JPS will list all the applications that are currently running with the process ID that you need. For example, something like this. And let's use something like JInfo. JInfo actually, at least on a Mac, requires you to run as root because it uses some privileged information. Here we go. JInfo with the PID. Right? So if you want to understand, or if your application is dependent, that happened to me once in real life, anything that the JVM is configured as, the key directives, which JDK is running, right? Happened to us one in production, something got misdeployed by accident. We were thinking, and I'll date myself, it was running 1.6. We were running on 1.5. All kind of weird stuff was happening. One of the easiest ways to find out was to see what the JInfo runtime was, right? And somebody mentioned JStack. So I'll show you what it is. One of the, again, easiest way to obtain a thread dump of a running application is via JStack. So do know your tools. They come in extremely handy. We will take the test tab. Where is it? And we can stop it. We don't need it right now. We'll deal with it later. Let's go back to the slides. Right, so we talked about the performance tuning cycle. In our talk today, we're going to run through the steps. So let's start. Imagine, if you will, and I'm sure for most of you it's a hypothetical environment, your sales team comes to you and says, hey guys, customer is complaining. We sold them something on the performance. It's supposed to finish in about, let's say, sub-second, 700 milliseconds or less. You go, okay, what is it? And imagine, and again, you have to understand, my examples are conference examples, so they will be trivial, and the performance problems in them are not necessarily the real performance problems. The key here for the talk is to talk about the tools and how to find that magical vector into the code. So it helps that when you prep for the conference, you start with an unoptimized code, which we will do. And we'll start with this piece of code that, let me assure you, does not run in less than a second. In this case, 2,900 milliseconds, right? Now, couple key things that you see about this app, right? When I started, it waits for me. It does a bit of a warm-up. If you try to tune an application, not an individual piece of code, sometimes you want to let it warm up. So all kinds of things happen in the virtual machine when you just start, right? JIT compilation happens, memory caches get warmed up. So depending on what is that you're trying to tune, you may want to figure out how to get your test up into a stable environment. In my case, it's just a piece of code that does some warm-up, right? In my case, it also waits for me to press enter because we're talking about seconds here, and I want to be able to attach some tools. So when I press enter, something happens, that something creates a dot on the screen for every several hundred iterations, and then it says, how long did it take? So that's the app we're going to try to get to less than 1 second. The other context we're going to talk about when it comes to performance tuning is this concept of a, am I stuck in a loop here? Here. We're going to talk about this concept of a dominating consumer. Typically in every performance problem, there's one thing that dominates the performance of a code you want to optimize. This was nailed or coined by a gentleman by the name of Kirk Pepperdine. If you're interested in more content on performance tuning, do look at his talks. But the dominating consumer is typically one particular item that is easy to measure. It could be garbage collection, could be CPU, could be system memory, etc., etc. And that's something that we're going to look for. So in this particular case, I know it runs for 3 seconds. Let me just get a new shell, right? We know that this thing, where am I? Nope, that's not where we're going to be. So we know it runs for 3 seconds. We need to find the dominating consumer. I typically like to understand what happens with the CPU first. And that's what we're going to do. We're going to start with the CPU. Knowing your operating system is important. On a Mac, you have this lovely tool called Activity Monitor, and it has this lovely window called the CPU history. And the CPU history will chart the usage of the CPU over time, right? And it will do so in 2 colors. The green color is what your operating system spends in user space, actually running your applications. And in red is what is it doing in kernel, system time. So let's see what happens here. So there's a CPU spike. It's a powerful machine. It's a 4-core machine. Let's actually run it and see what happens. Can anybody tell me if anything looks peculiar? I have 4 CPUs on this machine. How many of them have been utilized to run this application? 2. That's a first hint, right? I have this powerful server, and something is going on in that powerful server that doesn't allow me to use all the CPUs. To try to figure it out today, I'm going to show you a tool that is available for free called JVisualVM. Has anybody used it before? Wow, that's progress. The first time I did this talk, it was much light to utilize. So this is the tool. You can run this tool both locally and remotely, so you are able to attach to remote servers. You just have to poke some firewall holes. So we're going to find my app. So here in JVisualVM, you have some fundamental stuff, right? You have the JVM, what's running. You can also look at system properties like you would in JInfo. Not very interesting for us. You have some basic monitoring on CPU usage and garbage collection activity. You have some basic memory maps and thread allocations. You can initiate things like a heap dump, which can be useful. You can look at the threads. And that's where we're going to start. I have few plugins installed on this instance, and there are a couple useful plugins that I wanted you to show. So what I have is VisualVM TDA, Thread Dump Analyzer, VisualVM Garbage Collection, and Thread Inspector. Those are the 3 plugins that I'm using. You can easily download them. Some of them download automatically. So in this view, we're looking at JVisualVM and a thread map. And let me run this thing and see what's happening. So clearly some bunch of new threads materialized. So you can see, unfortunately, you cannot change the fonts, right? They're called pool 2 thread 1 through 8. Clearly there's some kind of thread pool in this application. What do you guys can tell me about how well this thread pool got utilized? Not well. Why not? No, like we don't know about system time. We're just looking at the threads. Why do you think it's not well utilized? Who said no? Somewhere here I heard. Yeah. Why is it not well utilized? Yeah, only like 2 threads concurrently at most run. That kind of defeats the purpose of having a thread pool, right? So a bonus question for a t-shirt. What do I need to do to find out why not all threads are utilized? What's the next logical thing to look at? What tasks are blocking? How do you do that? Thread dump. Who said thread dump? Okay. I've got plenty of t-shirts. Oops. All right. So Again, remember JInfo if you're on a console, but JVisualVM does provide a handy tool. So we're going to close this because the run is over. Start it again. Attach. Right here, in one click, I can take a thread dump. Right? I don't need to overthink any of this. Awesome. Here's the thread dump. They're easy to read. If you do it a lot, you will find something. Because I'm lazy, I use a plugin. So I have this thing called the thread dump analyzer. And if you look at it, it will look at my dump and organize them. Let me just resize this. So here we are. We have 28 threads overall. 6 of them are waiting on a monitor. Here they are. Oh, look. This is a thread pool waiting on a monitor. Magical. And if you see when I change the thread at the bottom, you can see this thread dump. Let me just move it a bit so you can see it better. Right? What do you see? They're all waiting in the same place. Remember when I talk about looking for the tools that give you the vector into the code? This is my vector into the code. This is a 40-line application for the demo purposes, but this could be a multi-million line app. And I know that next place I need to look is personstore.java line 23. Let's do that. So we're going to go to IntelliJ. We're going to go to person store. And we're going to look at line 23, which is in this method here. So, looking at this code, anybody strikes you odd? Clearly somebody tried to write a cache of some kind. Rule number 1 on writing caches. Does anybody know one? Don't write caches here. I got some stickers for you. Do not write your own cache. But again, remember, we're trying to fix a performance problem. We're not trying to boil the ocean here. So we're going to fix this cache, right? Why? Because if you look at it, every access to this cache is synchronized, both reading and writing. Probably not a good thing, especially since the cache, things in cache are meant not to change a lot. So if you want to read from the cache, what's the point of synchronizing it, right? Who knows what other options we have to change this code very, very little to fix this synchronization. Concurrent hash, excellent. So we're gonna, like in a good cooking show, grab a pre-cooked piece of code. Here we go. So this is concurrent hash map, right? Didn't do anything. But we took the synchronized blocks out. So let's remember our tuning cycle. Measure, identify, fix. What's next? Measure. Excellent. So without tools, without anything else, we're going to compile. Because without compiling, there's nothing to measure. We're going to run. Not bad. 2.9 to 1.1 was one free tool, and importantly, looking at the right place in the code, right? Not quite there yet. We still have a way to go to reduce the performance of this application, right? So let's see. Let's reset it up again. Let's go to Visual VM. Let's connect to the new app. Let's look at what else is going on. Remember, our first dominating consumer was in the CPU. We could max the CPU. Actually, let's not do this yet. Let's not measure it like this with Visual VM. Why don't we look at the CPU again? Because if our theory is correct, we also should be able to utilize all 4 CPUs, right? So let's see what happens there. So we're going to warm up. Going to go to the CPU. We're going to clear it. Much better, right? You see the spike of all 4 CPUs. I still see that an app that does something very basic has a lot of red down here, right? Red is system time. Red is when you go to the kernel. Red is when you try to obtain a lock, right? This is what happens when you have to typically go to the kernel. So let's see what else it could be. So let's run it again. Now let's run it with Visual VM. Other reminder, sometimes it's tempting and sometimes I myself make a mistake of trying to run testing while having tools attached to the app. Well, that's a bad idea because those tools, as you'll see when we get to the profiler, they change the behavior of the app substantially. So why don't we look at a few other things? So we have this monitoring. Let's look at this. So we have a spike in live threads. That's the thread pool starting up. We obviously have a bit of an increase of memory on the right here. And here we have an interesting thing happening. Out of the 32% of CPU that we've used overall, we spent 10% doing garbage collection, apparently, right? 3.5% out of 35 was garbage collection. Seems kind of high. I also have another lovely plugin called Visual GC, right? So I can see how many collections have happened. So 10 collections have happened in this span of second, right? And allocation failure, last cause, means, well, because I've run out of memory. I need more memory, so I needed to collect some stuff. Interesting. So who knows, what do you do when you run into an issue with garbage collection? What's the next logical thing to look at? JMX? No. What else? Somebody said the logs over there. What log? GC log. Awesome. Let's get you a t-shirt. Almost. My apologies. Who knows how to enable GC log? JVM parameter. Something like this. X logs GC log. Print GC details. Print GC timestamps. Right? Now, little story about this for those of you that have been coding a lot. For whatever reason, the creators of the JVM many years ago decided that the way to index the garbage collection log is in seconds from the beginning of the JVM time, startup time. That helps, right? Especially when you wake up at 2 a.m. in the morning when you're on call on Friday, and in the log it says bazillion seconds and 35 since the beginning of the JVM, and then you do this mental mass acrobatics trying to figure out. When I look at this log and it says 1,745 seconds. What time of the day is that? Fortunately, the creators of the JVM at Oracle finally heard this, and the GC timestamps are now in real time. So we can now do something like this. So we'll start the same app. And this is actually not the same app. Stop. Here we go. I actually already had GC log in run sh. Oh, I didn't. We will add it in a second. Live coding on stage. Here, we cut from here. And we add there. There we go. So run sh will produce a log. Let's confirm that it's here. Here it is from a minute ago. Let's look inside. Looks something like this, right? Not very useful tool. I'm a big fan of using visual tools, but at least it gives me something. We'll show you another visual tool for looking at the logs and analyzing them. But first we'll start from running this again. In the right place. Attaching Visual VM. Visual VM, thanks to Oracle, for a long time have been shipping with a free NetBeans profiler inside. And that's what we're going to go to later. I know that I'm generating a lot of data. I don't know where. So we're going to go to the profiler, and we're going to use the memory profiler. And in the memory profiler, you have this useful setting. If you stop it, it will tell you that you can set this little checkbox has profile object allocations. And more interesting, you can have another setting called record allocation stack traces. So not only will it figure out where you're allocating the space, it will give you that magical vector into the code. So let's do that. So we'll start the profiling. It will finish instrumenting stuff. We'll do the run. magical details should start populating on the screen at some point. And if the demo fails, we'll restart it again, like we always do. We don't need this anymore. Application terminated, profiling results, and profiling results are empty, which is awesome because this sometimes I guess Visual VM has bugs. We'll try it again. So demo up, profiler, settings, make sure that everything is here. Hit memory, wait for it to finish its instrumentation, and run. Ah, here we go. All right, so what are we seeing here? So this is what it found. Objects that have been allocated during this test run. Here we go. Yes, thank you. Don't show this message again. So here's our snapshot. We'll move it a bit to the left. Right, we have... What is going on here? One second. Make sure we have the right code here. We do. We compile. If you ever want to be a conference speaker and you want to try the scariest thing ever is do live demos on stage. So what Visual VM is supposed to give us, if everything works well, is the vector. I think I did. Here we go. Object allocations. Save. All right, let's try it one last time. It's always nice when the demos work right before the talk, and then here we go. Now we're talking. So we have strings. No. We have strings and string builders being allocated 3,960,000 times. Seems like a lot for 2 seconds of execution, right? String and string builder. Now the beauty of this is you can double click and it doesn't have a source, but you can right here. What did I do? I broke JVisual VM. So you have to trust me on this one, and I'll show it to you. I don't want to spend time. Right here, there's a stack trace. You can right click on an object and it will record the stack trace allocation. And magically enough, we're back to here. This is the place that allocates a lot of strings. It will put you back into the same method, into the same vector. I want to show you a few more things, and if we have time at the end, I'll show you how to do that. What do we see here? Why do we think we're allocating a lot of strings? String concatenation in a cache key. Every time we read and write to the cache. That's a lot. How do you solve it? Sorry, interning the string. Who knows what is string interning? Okay, so interning of the strings, on the JVM there's this, on the string class there's this method called intern. It puts it on a cache. It used to put it on a special part of the cache, special part of the heap, not anymore. And it implements what's called a flyweight pattern, right, where you have a singleton for every instance of the cache. That could work, but interning in general is a risky thing because you may be running out of memory in other places, but a bonus point and stickers for knowing what interning is. What other options, what other way can we create the key that doesn't require creation of 1, 2, 3 strings or writing a string builder every time? Yes? Maybe with some Apache, no, yes? Instead of char use string, but map of map, no, yes? No. Using hashes? Closer. Hold on a second. We're going to go another. Yes. Well, the string is already in the person, but I need a cache key. Oh, somebody said the magic word. Special class for the key. Or as we call it in software engineering, create a surrogate key. Ideally something more friendly. And like in a good cooking store show, I have created one. It's called a person key. Here it is, right? This way I can construct this key every time I go to the cache without having to create new strings because they're read-only, right? Now, I have to do the right thing. What do you have to do? Absolutely. What happens if you forget those two methods, the hash code and equals? Hopefully everybody knows, right? If you don't implement this, all kinds of weird stuff starts happening. Do I know if this is the most optimal way of implementing those things? Probably not, but by the way, I don't care because I haven't seen that this is a performance problem yet. So all I have to do is change the code, and now instead of concatenating the key for the string, right, we create a new person key class, we give it a first and the last, and magic should happen. Let's see if it does. Don't forget to build, as they say. And we will run again. Hold on a second. Let's do this. Did I save everything? Person store. Keys. Gradle build in the right place. And run sh. 1.4. Okay. No. Let me make sure nothing else is running here. Something's weird's going on with my computer. Hopefully not time to install updates. I am, you know what, Gradle clean. Oh, I know what happened. I changed the system. I added GC logs and they're not free. So this is what we're going to do. Remember, when you observe the system, you inadvertently can change what the system does, and that's exactly what I've done. No. We will profile in a second. Something is happening that is not supposed to happen. All right, let us profile. Magic happens when you do live demos. Let's profile. We've got this working, allocations and GC. All right, this is good. Well, we certainly know that we're no longer allocating strings anymore. We're just allocating person keys, right? And you can see that we only allocated 25,000 of them. I will get back to it again. I want to show you a few more things before we figure out why I cannot get this to sub-second, because that will be a significant failure of optimization, because it's supposed to run in 700 milliseconds. And doing this, by the way, doesn't help. Like repeating the same thing as I'm doing right now is not helpful. But let me show you another example. Sometimes this happens. In the middle of the night, you get a call, or on Monday, you get a call from a customer. It says, hey, did you guys know that last time, like in the middle of the night, something didn't work? You go, no, we don't. Well, you look at the logs, you see something like this, you know, GC overhead happened. And you go, well, I guess we ran out of memory. We had a monitoring system. We had a watchdog. It restarted the system. That's normal, right? The question becomes, what do you do now? How do you find the root cause of the problem? What do you need to start troubleshooting something like this? Heap dump. How do you get a heap dump in the middle of the night when you don't know when it's going to happen? We're going to go to the person who raised their hand behind you. Heap dump on error JVM parameter. That is absolutely correct. It's a very handy feature that the JVM has. It says, hey, if you run out of space, save a heap dump. It is painful, especially if you're running a real-life application and you may be allocating, I don't know, 32, 64 gigs of RAM. It's a lot of space. It takes time. Customers complain. You're probably going to get pushback from your operations department, but the app is going to be down. But the answer is yes, but the app is not down, wants to get this giant 64 gigabyte file. By the way, thank God they're easily compressible. On disk, I will never find the root cause of the problem. One thing to be careful with those heap dumps, and you need to be aware of, is because you're dumping raw memory of your applications, you may be containing sensitive data like PII, credit card numbers, encryption keys. So you have to figure out what is appropriate for your company if it only happens in production, and how do you get this thing out of the production environment to your computer where you can troubleshoot effectively and safely without compromising the customer data, right? A lot of people, I've seen those heap dumps being dropped on Dropbox. I go, do you guys really know what's inside? So here we go, right? The JVM did what it's supposed to do. It created this heap dump. So the Visual VM has a tool that will allow you to look at heap dumps. It's fairly rudimentary. You just go here, file, load, and you load a heap dump through this thing. It's not very interesting. I'm a big believer in this tool, and it's called Eclipse Memory Analyzer. Anybody use that? Wow, that's progress compared to a few years ago. That's much better. So if you haven't, it's a nice tool to play. It's probably the best tool I know for analyzing heap dumps. Here's the one that we just dumped. Let's just make sure this is 566. Here we go. Now, this tool requires a fairly powerful computer. We are opening a toy heap dump. It's like 100 megs. If you're opening a dump of 32 gigs, you're probably going to need at least 32 gigs of RAM, maybe more, right? So keep in mind, you need a special environment to use this tool. And this tool will give you a bunch of stuff out of the box, right? When you first open the dump, it goes, hey, I can run a bunch of the reports. I'm going to do the leak suspect report because I suspect that there's a memory leak in there. So, and the good news about those reports, you can run them in the background, and once you finished running them, unfortunately, Visual VM creates, Math creates a bunch of files like this, where it saves a bunch of helper files. But the good news is, after you spend a lot of time running them, you can reuse them. So if I close this heap dump and I reopen it, you can still look at this stuff. So for example, in the overview, I'll show you a few other reports. There's this awesome report called the histogram, where you can see what's on the heap. So in my case, again, there is 1 million strings. Seems to be a common problem, and some kind of demo person with 500,000, so, you know. So I can see what's going on. You can also navigate here easily and see what's happening. Unlike a debugger, where you can look at an object and navigate down, in this tool, you can also look up. So you right-click and say, give me the list of objects with incoming references. So for example, if I look at this person object, I can see that the only reference on the heap to it is the value which sits inside the hash map, right? Which sits inside the hash map entry, which sits inside the table of the hash map, which sits inside the cache. The cache again. Which sits inside the cache member of the demo app class, right? And you can inspect the objects here, right? You can look at inspector, you can look at the root, you can look at the attributes of the object that we're inspecting, for example, the cache, right? So very easy to navigate it. It also has very useful reports. So for example, if you want to see who may be holding paths to this, there's this concept in heaps called garbage collection root, the top object that holds all the references. This tool knows how to calculate it automatically. So in one click, I can run a report, right, that will tell me for this object, who holds access, all the roots for this class, right? And again, the magical cache here. So like the tool before with Visual VM, heap vector into the code, we know that we need to look at this cache. Demo up2 weak cache. Why don't we do that? Demo up2 weak cache. So here's the code. Who knows what a weak hash map does? Right? I thought a gentleman in a light sweater over there. Yes. Or did you just raise the hand for the sake of raising the hand? Okay. So weak hash map is this magical map that will start releasing the keys when GC needs it, right? Sounds like a great idea to build your own cache, right? No. So why do you think in this case the memory never gets released? Yes. So the answer was because values are strong references. No, you don't need to. When you put something into the cache, yes, you were. Correct. The key has to be the weak references, and this little key that we have, right, the get first, that comes from the person class, is also inside the person class. So we have two references. So what you thought you wrote as the magical cache will automatically get purged in one line of code, and you were the hero, is not really it. So bonus question: what's the cheapest way to fix that? I will cheat. Don't write your cache, but like this is not my app. I was brought in to help troubleshoot the performance of it. And again, I'm not trying to boil the ocean. I will fix it easily. I'll just wrap it in another string, which creates a copy of the string. References get broken apart. Let's find out if that actually happens. Let's see if this demo. Oh, let's see if this demo actually works. Well, apparently you can make the demo work if you type everything in all caps. All right. So let's see. Voila. And it will run for a long time. The lesson here is not the specific ways of not creating your own caches or using the strings to hold weak references for the cache objects. The lesson here is to know the tools that will give you vector into the code. One of those tools on the market, or one of the categories of those tools you can put on your production environments, are a group of tools called APM. So if you guys heard of New Relics, AppDynamics, CA APM, or Dynatrace. The other one is this wonderful tool from a company called Zero Turnaround, XRebel. Anybody using XRebel here? Oh. If you have any bugs, complaints, or concerns, there's a gentleman on the left who'll select the winner. Anton, raise your hand. Who used to be the founding product manager of XRebel. We have an XRebel t-shirt. Anton, who had the best answer or the question so far? Who gets the t-shirt? The weak hash map. Who resolved that? Voila. And if you have any complaints about XRebel, Anton is here to listen. That's why he comes to conferences. So the key is to understand your environment, know your tools. I will do one more attempt on my previous run and figure out why it didn't go. In the meantime, I can try to answer any questions. Yes, over there. So the question was, I heard that the Java 9 Visual VM doesn't work with that. So not a true story. Number one, if you look at the Visual VM, it already does work with Java 9. My demos were Java 8. Visual VM has been an open source project for a while. The reason for that is when the JDKs, two JDKs that Oracle had, and that happened while I was still working at Oracle, the JRocket and Hotspot got merged. JRocket brought this thing called Mission Control. And Mission Control has a lot of duplicated functionality. It used to be a paid tool. Now it's a free tool for most of the things you would want to do. And that's why Oracle decided not to maintain two. So Mission Control is another alternative with the modern JDK. What else? Yes, over there. So the question was, what features would you like to add to Visual VM? Quite frankly, I haven't run into anything. It can be tough to attach to fast-running applications, so maybe figure out how to get this pause. Like I had to code a special pause, but beyond that, it's a tool that survived for the last 10 years, survived quite well, right? Basic or not. One feature that may be missing, there's this other tool that I didn't show today called GC Viewer that visualizes a garbage collection log. There used to be a plugin that used to work, but it doesn't. So having a plugin for garbage collection to logs in Visual VM could have been handy, so I don't have to use the tool. What else? Yes, over there. The question was whether the introduction of compact strings changes the way I think about performance tuning. It may change the things I look for, but fundamental process of reliable measurement, look for the dominating consumer, look for the tool that gives me the vector into the code, does not. Right? And by the way, what I showed you today applies not just to Java. I used to manage projects that were written, unfortunately, in .NET. Different tools, similar approaches. The key is not to fix the things you cannot measure, and ideally you find the things that you want to fix with the tools that give you a very specific place to look. That's one. I'm a huge fan of products like XRebel or APM products like AppDynamics. I used to be, when I was running an engineering team at Taleo, I was the third customer of AppDynamics because on production I had a profiler running with 3% overhead on my production environment that could show to my developers like, you know what, when your code is slow or when something is not running as well as it should be, there's your problem, right? And those are the kinds of tools I encourage you all to look if you want to do any kind of application at scale performance tuning. We have time for one last question. So the question was, what is the rule of thumb when you have a complex environment and you have to have a trade-off between tuning or adding resources? Well, the rule of thumb is simple: money. Because none of those resources are free. Quite frankly, if you don't have a good handle on a performance problem short term, throwing resources at the problem short term is a very viable thing to do because you have customers who may be screaming at your ear, and it's much easier to tune or troubleshoot the system when they don't do that. It also takes time sometimes to find the root cause or catch the right garbage collection heap dump, right? Or catch the right situation. So sometimes throwing performance at the problem, throwing resources at the problem is easier, but you're masking the problem, number one. Number two, in this day and age, a lot of companies will be competing on how effectively they can operate your environment. I'll give you an example. Anybody here uses WhatsApp? WhatsApp, on the day of the acquisition by Facebook, I know the guys pretty well, some of them are my friends, 72 servers was the footprint of what was running WhatsApp when they had 200 million active users, right? Sometimes being efficient with your capital helps. So my advice is don't do that for free, but understand what are your criteria. Like if you have an architecture team or if you have a business approach, you have to decide how much you can afford to spend on resources, and then you optimize within that. And if you're bumping, for example, in a typical SaaS product, you have about 10% of your revenue to spend on operating it. So if you can do it within 10%, throw the resources at the problem. If you cannot at some point, you have to start optimizing. All right, with that, I thank you guys for your time. Apologies for a failed demo, and I'm around.